In section 1.3, we're going to look at expected loss, decision rules, and risk. So since we don't actually know the loss incurred even after a decision has been made, we deal with the expected values, expected loss, and then later on with no data. When we have data and we look at more classical types of decisions, we'll look at something called risk and look at the expected value of that. The Bayesian expected loss, okay, so what we do is we start with our loss function, right? We have a loss, and that is a function of theta and the action. But since we have a distribution on the parameter space, on the thetas, what we can do is we can take the expected value of that loss function, and that will integrate out essentially the thetas and give us just a function of A. Okay, let's look at an example of calculating the Bayesian expected loss. We'll go back to the drug example. Recall that we had identified a loss function, and we will just calculate the Bayesian expected loss using the prior distribution that we also discussed earlier. So again, the Bayesian expected loss will end up being a function of little a, and so using the prior distribution in this case on theta 2, we're going to take the expected value. So we integrate as theta 2 goes from 0 to 1, the loss function times the prior distribution. And recall that the prior distribution is 0 everywhere outside of this open interval between 0.1 and 0.2. So we can just modify our limits of integration and put 10, which is the constant from the prior. Okay, so at this point, to evaluate this integral, we have to be careful how we handle the little a and the relationship between little a and theta 2. So first of all, we're integrating as theta 2 varies from 0.1 to 0.2. I've kind of indicated that over here in this diagram in red, and then in green, I've tried to indicate the three cases that we have to consider. So the first case is what if little a is less than or equal to 0.1? Well, in that case, little a will always be less than or equal to theta 2. Similarly, if we look at this case where little a is bigger than or equal to 0.2, then a will always be bigger than or equal to theta 2. Of course, the remaining case is, well, what if a is between 0.1 and 0.2? Well, then in that case, sometimes theta 2 is less than or equal to a, and sometimes theta 2 is bigger than a. So in that case, we'll have two parts to the integral. So let's see how that plays out. So let's consider the case where a is less than or equal to 0.1, and recall that in that case, a is always less than or equal to theta 2. And so if we go back to the definition of the loss function, in that case, the loss function is equal to theta 2 minus a. All right, the next case is, well, what if little a is between 0.1 and 0.2? Well, in that case, we'll have to integrate over the part where theta 2 is less than or equal to a, and then plus the part where theta 2 is bigger than or equal to a. And then we'll have two integrals as you see there, and in each case you just have to make sure that you get the loss function the way it should be. And so the last case is if little a is bigger than or equal to 0.2, and in that case, little a is always bigger than or equal to theta 2, and so you look at the definition of the loss function and you see it's 2 times this difference. And so now we have the three expressions that apply for the three cases. And then you just evaluate these intervals to put together what the loss function is. And so you should get what you see there. Okay, so that's an example of calculating Bayesian expected loss. Now let's switch gears and look at decision theory a little bit from a classical point of view. So let's look at the frequentist point of view. And so the first thing we want to define is what a decision rule is. So a decision rule is typically denoted with this lowercase delta that you see there. And you can see that it is a mapping from the range space. And the range space, of course, is the set of possible values that your data could be. So what your random variables output to the action space, because that's what we do with a classical decision rule. We take the data, the x's, and then based on what that is, when we make a decision, we take an action. And so a decision rule is just essentially a mapping defined in that way. And we say that two decision rules are equivalent if the probability that they are equal is equal to 1 no matter what theta is. And so if we have a particular realization, as you see here, if we know that our data turned out to be little x here, right? The standard in statistics is that when you see a capital X, that is random. When you see a little x, that's a realization. That's some actual, that represents actual data. And so if this is what we observe, then delta of that little x is the action that we take. Okay, so let's look at an example of classical decision making. And this is something that I'm sure we've all seen. So this is a very common situation. So assume we have sample data about theta 2, and we suppose that we interviewed little n people in order to determine the number of people that would buy the drug. So we referred to this earlier. And we said that reasonably, this random variable should follow the binomial distribution we see here. And so the standard decision in classical statistics is what you probably would recognize as p hat. That's usually what this is called. It's a proportion of successes from the little n trials. In this case, it represents the proportion of the people surveyed who said that they would buy the drug. And so from a classical point of view, that's what you would do in order to make a decision about how we should estimate this unknown proportion. So the risk function of a decision rule, a classical decision rule, is what we see here. So we take the expected value of the loss function with respect to x. Remember that superscript tells us the expectation with respect to which variable we're taking the expectation. So in a sense, we integrate out the x, we integrate out the data. And so what we end up with is the risk function, which is a function of theta. So that's an important thing to note. The risk function is a function of theta. But of course, theta is our unknown, and so how do we utilize this risk function? So the idea is, let me get a little space here to work with. Before we look at the next definition, I just want to hopefully help you to understand the idea here. So we've got theta, it is our input. We can think about that as our independent variable, and risk is the output. And so one risk function might look something like this. and a second risk function might look like this for two different decision rules. And of course, risk, as its name implies, is something that we want to minimize. So if you look at those two curves, which one would you want to go with? Well, it seems obvious that the red curve is worse, right? Because for every value of theta, no matter where we are, the red curve decision rule has more risk than the blue curve does. Okay, so let me clean this up a little bit. So in those, comparing those two is there's no problem to see which one is the better one. How about let's say I need another color here. How about this decision rule with this risk function here? Now which one is better, right? Because we've already said the red curve's not even being considered, so we're just going to scratch that out. But now look at the orange decision rule risk curve and the blue decision rule risk curve. Can we say which one of those is better? And of course, obviously the answer is no, because in some places the risk of one is higher, and then in other places the risk of the other is higher. So this is the idea of the next definition. So we say that a decision rule delta 1 is R better than delta 2 if the risk function of delta 1 is less than or equal to the risk function of delta 2, and this is for all theta. And then also at some point there has to be strict inequality. And then we say that delta 1 and delta 2 are equivalent if they're equal for all theta. And that seems like a very reasonable definition for equivalency. We say that the decision rule delta is admissible if there is no R better decision rule. And otherwise, delta is called inadmissible. And we saw that earlier. Remember, with the red curve, it was inadmissible because we could do better. But then with the other two, there was no clear winner there with the other two. So in my example earlier, those last two that I drew were both admissible. In this course, we will only consider decision rules that have finite risk, and we'll call this set Fancy D. So as you can see there, we'll call this set Fancy D. And again, we require that the risk is finite for all theta.